Okay, so far we've been doing definitions. Let's actually try to do some proofs. So how do you prove things about sets? So let's try to prove some theorem that will probably look familiar. In particular, let's prove a simple theorem that says the following. So the purple area on this picture can be described two ways. One of them is to say you take a union of A and B, and the purple area is everything that's not in this union. So it's a complement of A union B. Another way of describing it is to say if I take everything that's not in A, everything is not in B at the same time, this will be exactly the purple area, because things that are not in A but in B will be blue, not in B but in A will be yellow. If they are not in A and also not in B, they will be in the purple area. So here's how you would write it a bit more formally. You could say, in general, for any sets A and B over any universe U, complement of A union B is equal to complement of A intersection with complement of B. So what are we proving? We need to prove that two sets are equal. What does it mean for two sets to be equal? That means that they have exactly the same elements in both of them. So that means that all the elements of the first set are in the second set, and all elements in the second set are in the first set. And this is generally how a lot of proofs about sets will go. When we need to prove that two things are equal, we have two parts going two directions, and each separate directions can be proved using, again, logic, by using the definitions of what it means to be in a set, what it means to be in a union or a complement or an intersection of sets. So, for example, when we are proving that set C is a subset of a set D, what we need to prove is that for every element X, if X is an element of C, then X must be an element of D. So let's try it with our example. So here is our theorem for any sets A and B in the universe U. Complement of the set A union B is equal to complement of the set A intersect with complement of the set B. Let's do the proof. So first we need to prove that the first set is a subset of the second. So complement of A union B has all of its elements inside complement of A intersect complement of B. And here's how the proof will go. First we say let's take any element, arbitrary element of complement of A union B, and our goal is to show that this element must be in the set on the right hand side. Now we are going from sets to logic by using definitions of complement, union, and intersection. What does it mean for A to be in complement of A union B? It means that A is not in A union B. Something in the universe, but not in A union B. And what does that mean? It means that it's not in A, and also it means that it's not in B. And this is by De Morgan's law, because originally we say it's not an A or B. That means it's not an A or not in B. Now using De Morgan's law, we get that X is not an A intersection, is a complement of A intersection with complement of B by definition of what it means to be in a complement. And we are done. And we are done because we picked an arbitrary X in complement of A union B. You see here we're also using universal instantiation and universal generalization and talking about arbitrary element. If you look at the book does it slightly different because they prove this theorem well before they introduce universal instantiation generalization. Actually, they do it even before they do logic. So they try to do it by talking about definition of the set builder notation. But since we already know this terminology, might as well use it. So let's prove the other direction. Again, we take an arbitrary x, but now of the right-hand side set, which is complement of A intersection complement of B, universal instantiation. By definition, what means to be in the intersection, x is in complement of A and x is in complement of B. So by definition of complement, it's not in A and not in B. So it's not in A, or it's not that x is in A or x is not in B by De Morgan's. Again, it's not an A union B, it's in its complement, and we are done. Finally, because we prove two directions, by definition of what it means for two sets to be equal, we have our equality. So does this equality remind you of something? Something that we actually did use in the proof, but for logic. So this equality looks very, very similar to the identity we had at the very beginning of this class, something that we did in the first lab or so. Negation of P or Q is equivalent to not P and not Q. So it looks like De Morgan law works for sets in the same way that it works for logic. Is it just De Morgan that is special, or is it some kind of general phenomenon? What do you think?